Hello everyone, my name is Jan, and today I'm here to present GROut. To distribute or not to distribute? That is the question. But first, a little bit about myself. I'm a second-year PhD student in information technology. I am currently working on the Oracle Labs and NextLab partnership, and I am an HPC intern at the Pacific Northwest National Laboratory. My main interests revolve around high-performance computing, distributed systems, and cloud computing. Let's talk about the topic of today, GPUs. We have all seen how GPUs have been adopted in a wide range of scenarios, such as genome analysis, weather forecasting, graph analytics, and molecular dynamics. And recently, we have all seen how GPUs have become the de facto standard into accelerating large language model training. The problem is the fact that while on one end, cloud providers have seen this as a great opportunity to offer to the end user multi-GPU resources and multi-GPU architectures, the required expertise to fully exploit them is still very high. And users in novel emerging domains might not have this expertise. Toward this problem, GPU vendors have tried to implement a unified virtual memory. That is the capability to have a unified address space shared among the hardware accelerators and your host, without having to worry about having duplicate pointers, manual memory management, and also the creation of batching mechanism to handle large-scale dataset. To do so, Unified Virtual Memory offers a capability called Unified UVM Oversubscription, that is the capability to access and use more memory regions that are bigger than the one into the hardware accelerator, therefore simplifying the overall programming paradigm. But let's see a case study, the Black-Scholes benchmark, where we have a benchmark that predicts the future stock pricing in the European market that is very massively parallel. And we don't have that much interdependencies between the kernels that are running. And we, on the right side of the slide, you can see that we have the execution times on two NVIDIA server-grade GPUs, the V100, with 16 gigabytes for a 32 gigabytes total. As you can see, switching from the 32 to the 64, we have a massive slowdown and massive degradation into the performance of the system. Here, you can see why we are going from 32 to 64, but the total memory available into the hardware accelerator is just 32. So we are actively using the unified virtual memory over subscription mechanism. And instead of doubling the time required to do such an operation, doubling the size of the dataset, we are going 100 times more. So how can a user simplify and also mitigate those slowdowns? One option is to use hand tuning of the unified virtual memory using memory prefetching or memory advices. And moreover, the other option is to, and by doing so, you are matching the unified virtual memory behavior and treating it like a black box model. That is a tuning that is workload specific. And therefore, it requires multiple trial and error cycles, and you have to redo it each time you change your workload, and also each time you change the dataset size and the structure of your dataset. Therefore, it requires a high expertise to highly fine-tune your application. On the other hand, a user might want to scale out its solution, reducing effectively the oversubscription of each of the hardware accelerators. To do so, the user can restructure its workload using common frameworks such as CUDA-aware MPI, Nickel, or NV shared memory, with an high engineering effort required to match those programming paradigms and to change and restructure its overall application. And therefore, this solution requires high expertise. The other option is to use GROut. GROut is a polyglot framework in the sense that it can be accessed from major programming languages such as JavaScript, Python, and Java, thanks to the GraalVM backend. On the other side, GROut offers simple and workload-agnostic APIs for the end user in order to write its application and distribute it into multiple nodes with multiple GPUs inside of each node in a transparent manner, and requires minimal expertise to do so. Let's see an example of the APIs of GROut. Here we can see that import the polyglot capabilities of GraalVM to use GROut. And then we offer the user the capability to compile at runtime its kernels, or either bind precompiled kernels or library to be used later on. And we compile a kernel called Square. The next step is to allocate some memories that is managed by GROut and therefore that can be distributed. And finally, the user just have to write its application in the same way that it was used to, with the same logic, with the same workloads. And in particular, in this example, there is only one kernel, but there might be more, there might be intricate interdependencies, and GROut transparently handle everything: the distribution of the kernels, the synchronization point, the guaranteeing of correctness. The architecture of GROut is an architecture that is composed around a computational element, or that is a wrapper around each kernel calls, access to libraries or to memory managed by the GPU, and it provides to us its polyglot interface. A computational element is then used inside of a controller that applies an internode scheduling procedure, that is using the dependencies between the different computational elements that are scheduled by the user to place the computational element into the best node possible. On the other hand, we have the worker, that is the lower level of scheduling. Inside of each node, there is a worker, and the worker applies an intranode scheduling procedure to place the computational element into the best device possible based on some scheduling and heuristic of the single system on the single node. We tested our system onto multiple workloads that, as you can see on the right side of the slide, have different interdependencies between the different computational elements. We have machine learning ensemble that has an unbalanced branches. So we have branches that take longer to execute, and we have branches that are on the other hand shorter. Conjugate gradient, on the other hand, has intricate interdependencies between the different kernels of the system, while lastly, matrix vector product is massively parallel. The first question that we try to answer is, are those workloads affected by unified virtual memory slowdown as for the Black and Scholes one? To do so, what we have done is test the workload that we have selected. And the first thing that we notice is the fact that by switching from an oversubscription of from a dataset size of 64 to 32 or to 64 to 96, we experience a deep increase into the execution times of the system in all of the different benchmarks, with matrix vector product actually reaching the maximum execution time that we have set onto inside of our evaluation. So the last question is GROut capable of reducing this steep increase into the execution times? And we tested GROut onto two nodes equally equipped with respect to the previous solution. As you can see, GROut drastically reduced the steep increase by going from a 70 times of slowdown, sorry, to a 4 times of slowdown. And in some cases 4 times, in other cases 13 times, but we are capable of reducing the oversubscription slowdown. So comparing the solution of GROut with respect to a single node solution, we can see that while we are saying under the 1x of oversubscription factor, it doesn't make really sense to go to multiple nodes. So here as a baseline, we have the GROut execution times, the single node execution times. And if we go just one step further, we can see that the benchmark starts to gain speed ups with respect to the single node execution while adopting GROut. And by the way, this is an end-to-end approach. So we are considering all the execution time, both for the scheduling overhead, network transfer, data aggregation. We are capable of offering 7 times, 24 times of speed up with respect to a single node execution. What GROut brings is a massive reduction on the complexity and the lines of code required to write the same workload, and it completely reduced the impact of the unified virtual memory over subscription, drastically reducing this impact for the end user. And it does so by having a transparent workload distribution. For what concerns future research direction, we are interested in investigating a polyglot remote direct memory access approach to speed up the exchange of data between the different workers, and moreover, among the scheduling part, to have an autonomous scaling procedure that can, at runtime, for the user, scale the number of nodes, for example, while keeping some KPIs provided by the user. So thank you for your attention. And if you have any question, just feel free to write me an email.